Is my screen visible?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
Only one is enough. If you do not see the screen, then you can tell me. Okay,
क्या
so
यहाँ पे ना नो वाले सीन ज्यादा बोलना पड़ रहा है क्योंकि
okay, so we have seen in the last lecture there are three types of elementary operations on the rows of a matrix. First one is multiplying the ith row by a non-zero constant C. The second operation is interchanging two rows. That means you can interchange row I with row J, which means you write row J in place of row I and row I in place of row J. And the third one is multiplying, replacing row J by row J plus some constant C times row I. Okay, so these three are elementary row operations. Similarly, we can also have elementary column operations. For example, we can have the column counterpart of the first operation is we can have jth column, replace the jth column by some constant C times Ci, where C is a non-negative or C is a non-zero constant. Similarly, you can have you can interchange the ith column with jth column of the matrix, and the last one is you can write Cj equal to Cj plus some constant type Ci. That means you replace the column jth column by the sum of the jth column and the constant time the sum the constant time the ith column. Okay. So the things that we are going to see from now onward will be mainly for the elementary row operations, but all the things that we see here can also be done with column operations. Sometimes the column operations are difficult to comprehend, therefore we always use elementary row operations in our we are going to use only elementary row operations in our subsequent discussion. Okay, so now we have a definition, this row equivalence. We say that a matrix A is row equivalent to a matrix B if matrix A can be obtained from matrix B by using a finite number of elementary row operations. Okay, and this is written as A is equivalent to B with this notation. So whenever you see A sim B, this notation, this means that A and B are equivalent matrices. Fine. So you perform some operations on the matrix. You perform one or more than one elementary row operations on the matrix B, and then you get a matrix A. This matrix A is said to be equivalent to matrix B. If you reverse the process, that means you reverse these operations on the matrix A, then from matrix A you can get a matrix B. Okay, so so we say that A and B are row equivalent matrices. You can do the same thing with the column operations as well. In that case, the two matrices are said to be column equivalent. Okay, so this is what is written. We can have the elementary column operations with similar notations. Okay, now let us consider an example of a row equivalence matrices.
Sir, column equivalent also have the same notation, right?
Same notation means whenever you see R, replace R by C.
No.
Capital R stands for row operations.
A equivalent to B stands for both row and column. So we have to check whether we can use row there or column.
No. So you don't have to mix the row and column operations together. You obtain matrix A from matrix B using only elementary row operations. Then it is said to be row equivalent. When you perform row operations, you do not simultaneously perform column operations. Both cannot go together.
Okay.
And similarly, when you perform these elementary column operations on matrix B, then you get a matrix A, which you call column equivalent. So by using the elementary row operations, you get the matrix A, this is row equivalent. By using the column operations, you get matrix A, this is a column equivalent. Fine, you do not have to mix. So you do not have to apply in one step you apply row operation, in the next step you apply column operation. This is not allowed. Okay.
Okay, sir.
So now we consider an example. Let us consider the matrix B given by this, and let us perform let us interchange row 1 with row 2. So what is row 1 in matrix B? This is row 1 in matrix B, and this one is row 2 in matrix B. When you interchange, you write row 2 in place of row 1 and row 1 in place of row 2. So your new matrix will be 1 2 minus 1 minus 1, which is row 2 in the original matrix B, and 2 6 1 7, which is row 1 in the original matrix B. Okay, so you have this you have performed this second operation, interchanging two rows. Now let us perform two operations. We replace row 2 by row 2 minus 2 R1. So what is row 2 here? Row 2 is this one, and row 1 is this. So multiply row 1. This is row 1 now in the new matrix, and this is row 2. So multiply row 1 by minus 2. So you have minus 2, minus 4, plus 2, plus 2. And then add this with row 2 to get row 2. So add them together. Add this one in the second row. So your first element will be 0. Minus 2 plus 2 will be 0. Then minus 4 plus 6 will be 2. So you have 2 here. And then 2 plus 1 will be 3. So you have 3 here. And then 2 plus 7 is 9. So you get 9. So this is now the new second row. Okay, so this you obtain from the operation row 2 minus 2 R1. Okay, now on the same matrix, we perform this another row operation, which is we replace row 3 by row 3 minus 5 row 1. So again, this is row 1. Multiply this by minus 5. So you have minus 5 here, minus 10, 5 and 5. And then add this in row 3. This is row 3. So you add them together. So add them. So what do you get? You get row minus 5 plus 5 is 0. Minus 10 plus 7 is minus 3. 5 and 5 plus minus 4 is 1, so you have 1 here, and 5 plus 9 is 14, so you have 14 here. Okay, so this is your third row. This is this operation that you perform here. Okay, so now you get this new matrix here. Now in this on this new matrix, you apply this operation. Replace row 3 by row 3 plus 3 by 2 R2. So what is R2 in this matrix? This is R2. This is R2. And this operation says that multiply 3 by 2 in R2. So you multiply 3 by 2, 0, 0 multiply 3 by 2 is 0. So you have 0. 3 by 2 means you get 3 here. 3 by 2 means you get 6 by 2, and 3 by 2 means 27 by 2. Okay? And then you add this. Sorry?
It should be 9 by 2, I think. You know, that 0, 2, 3 into 3 by 2 should be, I think, 9 by 2.
3 by 2
into 3 should be,
so 9 by us, the third increase. Okay, okay. Yeah. Thanks for the correction. So you have this this one, and then you add this with row 3. So add this with row 3 here. This is row 3. So 0 plus 0 is 0. 3 minus 3 is 0. 9 by 2 plus 1 is 11 by 2. And 14 plus 27 by 2 is 55. 55 by 2. Okay. So you get this new matrix after using this elementary row operation. So this is your new matrix. Now you can do the same operation, one more operation, that divide. Is there any question? Can you see this screen?
No, sir.
No, sir.
Sir.
No, sir.
No, sir. Somebody became the presenter other than you.
So do not become the presenter. Otherwise, this will disturb the class, whole class. Can you see the screen now?
Yes, sir.
Sir, yes, sir.
Yes, sir.
Okay, so now in this new matrix, you apply this elementary row operation, that is replace row 3 by 2 by 11 row 3. So this is your row 3. Multiply this row by 2 by 11. So you get 0, you get 0, you get 1. And 2 by 11 means you get 5. So your third row in the new matrix is 0, 0, 1, 5. Is this okay? So finally, after all these operations, you get a matrix and denote this matrix by A. So these two matrices are equivalent. The matrix A and the starting matrix was B. So these two matrices are equivalent, row equivalent, which we write as A equivalent B. Now, if you start from the matrix A and reverse this process, that means you start from matrix A, you apply this operation, I mean, you can identify the elementary row operations. That means if you start from matrix A and you multiply, reverse this process, you multiply this third row by 11 by 2. So you get this one. And then accordingly choose another elementary row operation so that you get this matrix. And similarly choose suitable row operations, 2 row operations to get this matrix, and then another suitable row operation to get this matrix, which is the original matrix B. So starting from matrix A, you can, when you apply the elementary row operations, starting from matrix B, you apply some elementary row operations to get a matrix A, and you can reverse this process as well. You can start from matrix A, choose the elementary row operations in such a way that ultimately you get the matrix B. Okay, so from matrix A also you can go to matrix B after applying some certain elementary row operations. Okay, so this is what that is why we always say that A and B are equivalent. So this is a symmetric relationship. From A to B you can go, and similarly from B to A you can go by using some sort of elementary row operations. Okay. So whether you write A equivalent to B or B equivalent to A, they mean the same thing, because from A also you can go to B, from B you can go to A. So both of them means the same. Fine. Now let us understand another important thing in this calculation. Now we start from an identity matrix of order 3. So you can consider an identity matrix of order 3, which is I is equal to 1 0 0 0 1 0 0 0 1, and then you identify some you apply these operations one by one on the identity matrix. So what was the first operation that we have applied in this calculation? We replaced R1 and R2. We interchange R1 and R2. Okay, so we interchange R1 and R2 in the identity matrix. So what do you get? You interchange this, your first row will become 0 1 0. So you have this identity matrix, and then you apply this operation interchanging R1 and R2. So you get your second row will become first row, second row will become first row. So you have 0 1 0, and the first row will become second row. So this will be 1 0 0. Okay, now apply the second operation that you have performed on B on this new matrix. So second operation you have performed on B is R2 minus 2R1. So this is your new matrix. You multiply the first row by minus 2. So you have 0 minus 2 0, and add this with the second row. So you get 1. 0 plus 1 is 1, minus 2 plus 0 is minus 2, and 0 plus 0 is 0. So this becomes your second row after you use this operation. Now apply this operation R3, replace R3 by R3 minus 5 R1. So R3 multiply minus 5 in the first row, 0 minus 5 and 0, and add this with the third row. So you have 0 minus 5 1. You get this one. Okay, so after using this these two operations, after using these two operations here, you get this new matrix. Okay, now let us do the next operation, which is R3. Replace R3 by R3 plus 3 by 2 R2. Okay, So when you do this operation here, you will get this matrix. And the last one is replace R3 by 2 by 11 R3. So you apply this operation here, you get this matrix. Fine. We denote this. So now all the operations that you have applied on the matrix B, we have applied all the operations one by one on the identity matrix. So from I3, now I get a new matrix after application of all these elementary operations, basically that we have used on B. The new matrix is I3 dash. We denote this new matrix by I3 dash. Okay. Now what we see, now what we do here. Now we calculate this product. We multiply I3 dash, this new matrix that we have obtained, by using the same elementary operations on B, elementary row operations on B. These operations are used on the identity matrix. Okay. So now we multiply I3 dash pre-multiply. So keep in mind this is pre-multiplication. Pre-multiply the matrix B, which was the original matrix, our starting matrix, by I3 dash. Okay, so I3 dash is this matrix that we have just obtained, and we are multiplying this by the matrix B. So when you do this multiplication, you get a new matrix, which is this. Okay, so matrix multiplication, everybody is aware, so I'm not going to tell anything about this matrix multiplication. You multiply first row by the first column, you get the first element, second row by the second column, you get the second element of the first row, and so on. Okay, so this is the matrix that you obtain by multiplying pre-multiplying I3 dash by the matrix B. Okay, now notice that the matrix that we obtained by this multiplication is same as the matrix that we have obtained by applying the elementary operations on the matrix B. Okay, this is exactly the same. We have this matrix B. We performed all these operations on the matrix B, and we obtained matrix A. Okay. Now we are going in different, we are doing the same calculation in a different way. We apply all the operations one by one in the sequence, in the exact sequence. First operation is this one, second is this one, third one is this one, fourth one is this one. Okay, so the sequence, you should not change the sequence. If you change the sequence of elementary operations on the identity matrix, then the result will not match. So you apply the elementary operations in the same sequence that you have applied in the on the original matrix B. Exactly the same sequence. Okay. So this product is also equal to A. And this is not surprising. And you also keep in mind that when you multiply this matrix I3, this should be pre-multiplication. If you do the post-multiplication, then it will become column element. This is equivalent to column elementary column operations. Okay, so that order should be fixed. So now we say that we can obtain matrix A from matrix B in two ways. By applying the sequence of elementary row operations on the matrix B directly. This is the direct calculation that we have first performed. And the second one is you do not perform the elementary row operations on the matrix B directly. Instead of doing this, you perform these elementary operations on the identity matrix in exact the same sequence. Then you get a new matrix I3 dash, pre-multiply this new matrix I3 dash by B. You will get matrix A. Okay. So these are the two ways you can obtain matrix A from matrix B. And these are the two ways to find the equivalence of two matrices. And this is not surprising because whenever you do the elementary operation on the identity matrix and you multiply this by the multiply this new matrix by the original matrix B, you get the corresponding elementary operations on the matrix B, and that we will see on the next slide. So before that, let us see another definition, which is called elementary matrix.
Excuse me, sir.
Yes. Yes. No, you have to see the order of the matrix also. So
Sir,
what is
how can we prove that
the order of the matrix is 3 by 4, right? So when you pre-multiply, that means row operation, you have I3. You start from the identity matrix of order 3. When you do the column operation, you do the column operation on I4. So when you apply this post multiplication, you do the post multiplication, you have 4 cross 4 matrix, and the product will be 3 cross 4. Fine.
sir, how can we prove that any two matrices are not equivalent always?
If you cannot get one matrix from the other using the elementary row operation, then they are not equivalent.
Yes, sir, but we can say that from an identity matrix we can create any given matrix, right? So how will we know in so many combinations that there is no such matrix?
No, so equivalence is related to the row operations only. You do not have to mix row and column operations.
Yes, sir, but in any identity matrix we can perform row operations and make any matrix out of it. But then how will we come to know that there is no such matrix to make them not equivalent?
Using identity matrix, how can you say that you can get all the matrices?
Like we can perform row operations and we can create many possible matrices out of an identity matrix, right?
No, but not all matrices.
Right, not all, because we have to take the constraint also. But still, I don't have a rigorous proof of that fact that no matrices will be equivalent then.
So if you're able to do this, then all matrices will be equivalent. So this is not true.
Yeah.
So basically, whenever you are able to get a matrix using the elementary row operations, then they are equivalent. Otherwise, not.
Okay.
Okay. All right. So now let us see this elementary matrix. Definition of the elementary matrix. So elementary matrix is a square matrix, and it is obtained from an identity matrix by performing a single row operation. Okay, so elementary the matrix of order m cross m is said to be an elementary matrix if it is obtained by performing an elementary operation, just one operation. If you do this row operation, then you get the elementary matrix using this only the row operation, and you can also do the column operation. Okay, so but the operation should be just one operation, not two operations. Like in the previous example, we have performed several operations on the identity matrix. Okay, so these are not elementary matrices. The only elementary matrix is in this operation is this one, because this is the matrix that you obtain by applying the single operation of interchanging row 1 and row 2. Okay, so this is known as elementary matrix. When you do the column operations, then also it is known as, then in that case also it is known as elementary matrix. So now let us see one example, couple of examples of this these elementary matrices. So you interchange row 1 and row 2, you will get this one. So this is an elementary matrix. In the in the identity matrix, so you have 1 0 0 0 1 0 0 0 1. You apply this operation, replace R1 by 3R1. So you get 3 0 0 0 1 0 and 0 0 1. Okay, so this matrix is also obtained by a single operation, that is 3R1 on the identity matrix. And similarly, you apply R2 plus 3R3. That means on the identity matrix. Yeah. Any question? So if you do not have a question, then please keep yourself muted. All right.
ऑनलाइन मार्च तक रहेगी फर्स्ट सेमेस्टर वाला.
Vansika, mute yourself.
अब ये प्रूफ ऑफ इनकम में क्या डालूं इसमें?
नहीं है तो इनपुट नहीं डालना.
कुछ नहीं डालना. चलिए फॉर्म 16 में भी ब्लैंक छोड़ दो. ITO.
Whosoever is speaking, mute yourself. Vansika. Vansika, mute yourself.
जो इसमें है वो ही इंक्लूड होंगी. चार्जेस है.
Okay, so now, so this is now you know what is elementary matrix. Elementary matrix is the matrix that you obtain by applying one elementary row operation on the identity matrix. Okay. So if you have a matrix A and you write this little e in front of this, so that means, and this little e is one of the elementary row operations. So you have seen 3 elementary row operations. So e is one of the elementary row operations that you perform on the matrix A. Then your new matrix is denoted by, let's say, E, A. Okay. So then there will be a row operation which we denote by E dash. If you apply this row operation on the matrix EA, then you will get the matrix A. Okay, so EA is the matrix that you obtain by applying the elementary row operation E on A, and then you apply another elementary row operation E dash on the new matrix EA, so you'll get matrix A. So there will be such E dash always. Okay. So now let us consider the same elementary matrices that we have, elementary operations that we have performed in the previous example. So we have, let's say, an identity matrix 1 0 0 0 1 0 0 0 1. Now, what are the operations that we have performed on B? First operation on B was interchanging row 1 and row 2. So apply this operation on this identity matrix, you get a new matrix which we denote by E1. Okay. Now pre-multiply E1 with B. So you get this matrix, and this matrix is exactly the matrix that you obtain by applying the elementary row operation R1 interchanging R2 on the original matrix B. Okay. Now what is the second operation that we have performed? The second operation is R2 minus 2R1. So second operation is R2 minus 2R1. This is the second operation. So apply this operation on the identity matrix. So what do you get? You get a matrix E2. We denote this by E2. Now what is the third? And then what you do? You multiply this E2, pre-multiply this E2 by E1 into B, that you have obtained in the previous step. Okay, so you have E2, E1, B. This will be equal to this matrix, and this is the same matrix that you obtain by applying this elementary row operation on this matrix. Okay. Now what is the third operation that we have applied on the matrix B? The third operation is R3 minus 5R1. So apply this operation on the identity matrix. R3 minus 5R1. So apply this operation on the identity matrix. So you get E3. Fine. And when you फिर किसी ने ऑन कर लिया. So when you pre-multiply this matrix by E3, you get this matrix, which is the same matrix that you obtain by applying the elementary row operation on this matrix, on the previous matrix. Okay. So now I will keep this and I will erase all these so that you can see where my pen is working. Now what is the next operation that we have done on the matrix B? The next operation on matrix B is R3 plus 3 by 2 R2. R3 plus 3 by 2 R2. So apply this operation on the identity matrix, on this identity matrix. So you get E4. Okay. So that means you multiply this matrix by E4, you will get this one, which is the same matrix that you obtain by applying this row operation on this previous matrix. Okay. And the last operation is on that we have applied on B. The last operation that we have applied on B is R3 is replaced by 2 by 11 R3. So you have R3 replaced by 2 by 11 R3. So apply this elementary operation on the identity matrix. Okay, so you get E5. E5 is this matrix. And then use this E5, multiply this E5, pre-multiply this E5 on this matrix. So you have this matrix. When you do this multiplication, then you will get this matrix, which is A, which was our which was the matrix that we have obtained by these operations on the matrix B directly. Okay, so what we observe from here? We observe from here that we apply the elementary, we identify the elementary matrices corresponding to each of these elementary operations. So we have performed all these operations here on matrix B. Okay, these are the 1, 2, 3, 4, 5 operations. We have performed 5 operations. Okay, so 5 operations we have performed, 5 elementary row operations on the matrix B in our previous example. So what we do now is what we are doing here is that we are performing these operations on the identity matrix one by one. Okay, so we have performed this first operation on the identity matrix to get the matrix E1. Second operation on the identity matrix to get the matrix E2. Third elementary row operation on the identity matrix to get E3. Fourth elementary row operation on the identity matrix to get E4, and the fifth elementary row operation on the identity matrix to get E5. And then you arrange this in the sequence. What is the first one? First one is E1, then second one is E2, third one is E3, E4, E5. And this sequence should be in the same order in which you have performed the elementary row operations on the matrix B. First we perform our interchanging R1, R2. So first you write E1, then you write, then you have performed the second operation, R2 minus 2 R1. Corresponding elementary matrix is E2, so you write E2 here. The third one is R3 minus 5 R1. The corresponding elementary matrix is E3, so you write E3. And similarly E4 and E5. So you should always maintain the order. If you mix up with the order, then this is completely wrong. Okay, so you always keep in mind that these orders should be this should be in the same order. Now, after performing this multiplication, you multiply this, pre-multiply this by B. Then whatever you get is the matrix A. Okay. Now this matrix that we have obtained by this product E. Pre-multiply E1 by E2, pre-multiply E1, E2 by E3, pre-multiply this E3, E2, E1 by E4, and pre-multiply E4, E3, E2, E1 by E5. Okay, or basically one can say that the product E5, E4, E3, E2, E1. This product, if you calculate separately, this product will come out to be equal to E3 dash. And E3 dash is the same matrix that we have obtained here. You can see that you will finally obtain this E3 dash. So E3 dash is E5, E4, E6, E3, E1. You can check this calculation by multiplying these matrices. Okay. So you have this thing. You can see that when we calculate this product, E5, E4, E3, E2, E1, this product will come out to be I3 dash. And this is the same matrix that we have obtained by using this elementary operations on the identity matrix in the same order. Okay. So you have another way to interpret this result. Okay, let me erase all these things. Yeah, this is coming again. I don't know why. Anyway. So from here, what we observe is the following.
Screen has gone.
Screen is gone. Can you see the screen now?
Yes, sir.
Yes,
No, sir.
Yes.
Yes, sir.
You can see everybody. If you are not, if you do not see, then say you cannot see. So everybody can see the screen. Okay, so from here, what we observe is that now let us say that this new matrix I3 dash, we denote this new matrix by P.
Excuse me, sir.
Yeah.
Sir, it is showing your screen share will never be stored locally or remotely.
You cannot see the slides.
Yes, I can see the slides.
You can see the slides?
I can see the slides, sir. I can see your screen, but not the slides.
Okay, so let me close the screen again and then I can share it again.
Sir, if you don't mind, can we do the next classes in MS Teams?
I will try, but I need your help also to make this MS team because I have around 120 students and it's very difficult to add all of them.
Sure, sir.
Or you already have an MS team?
Only
Yes, sir. All of the classes are on.
Yes, sir.
Classes are on MS Teams.
Oh yeah, the MS team is very suitable. But do you already have an MS team there? Like
Yes, sir.
Yes, sir, we have.
I am teaching.
Yes, sir.
Yes, sir.
Hang on a second. I am teaching S3, S4, S5, S6, S7. These batches. So do you already have a team for these batches?
Yes, sir.
You don't have.
We are not sure about
Links
it.
to the CRs will do the work.
Sir, you made a couple of us CR and said each batch should make their own team and add our teaching assistant last class. So we did that.
I need the CR to add everybody, not the batches. Like because I have to just make just a single team. Okay, so that means so I need somebody who can add all the students of the batches S3, S4, S5, S6, S7 in a single team, and then we can go with the MS team.
Sir, how will the CR get those emails?
Which email?
I think
Sir,
we
I
can
will have
directly
to
mail all the students of
so
any
that I can
particular
send them the
batch.
link.
एक करके बोलो. Which email?
Sir, I was saying that if we want to add everyone, then we need to have their email so that we can email them the link of the group.
I think using
Yeah.
this, we can get in touch with the students of all the sections. If we just do s3@iitr.ac or ac.in, then every student of S3 will receive that particular mail. So communication will be easier.
Yes, sir.
So you
This is
mean to
true.
say that I add a team here, create a team here, a class, and let's say this is name of the team is MAN-001. And then what do I do? How do I add the members here?
So the three dots on the right of MAN, you click on that, and then there will be an option of manage team members.
Three dots on the
Right beside MAN 001. Yes, sir. Manage members, and then here there should be an option to add. Yes, sir.
so you
Add.
if I write S3, no, I do not get. I have to write all
Yeah,
these
that I don't know, sir. I think you'll have to add it individually.
individually. So that is a very cumbersome task.
Excuse me, sir.
Yes.
Sir, like you send the batch, every student you send the mail of link. So in one such mail, you can send the invitation.
How do I do this? We can do it now.
So for that you'll need either you need to create a code or you can
No, you just guide me because I'm not that much familiar with this team.
okay, so you'll have to go in the same you just click the menu button, the three dots,
Yeah.
and then here just a minute.
Sir, if you see the chat, Arav Ratra has sent a email ID. So if we type s3@iitr.ac.in, so all the S3 members will receive the email.
So how do I do this? You asked me to.
Sir, actually,
Sir, you have to type this in Gmail, sir.
Sir, I can tell you how you can create a link from a laptop. So you can add me, and then I'll generate a link and send it to you.
Okay. Shall I open my laptop?
Yeah, that will work too. Or else you can just add me, and then I'll create a link and send it to you on WhatsApp.
So,
and then you can mail that link.
So you mean to say that I go to this three dot, then I write manage, then add, and then write your name.
Yes, yes, sir. Ayush. _A_Priyadarshi. Priyadarshi. Yeah, the last one. PRIY.
This one.
Yes, sir.
Okay. And now?
Done.
Done. Okay. So then?
Yes, sir. Now I'm added. So I'll get a link to the team, and I'll copy it and I'll put it on the group which you made for the CR, and then each CR can share
forward it
to their respective batches.
Okay. Okay. So and in that way they can join.
So you'll get requests. You'll get requests to add us. We'll click on the link and send you the requests, and then you can accept us, and we'll be in.
Okay. Okay. Very good. So that we can do.
Sir, I've sent the link to the MAN 001 CR group, which you made just for the math CRs.
On the WhatsApp?
Yes, on WhatsApp.
The better option would be to send a link in the chat box. Everyone can join now.
I'll send it on the chat as well. There you go. It's in the chat as well.
So you can just see if people can join. Try to join now.
So to accept the requests, there's an activity tab on the left bottom corner. So that's where the requests will come. Left bottom corner.
Left
bottom corner, sir. Activity tab. So all the requests should come here.
I am getting something on my laptop.
so on and so forth.
No, this is something else. Where is the team? Okay, so I think I'm getting something on this my laptop. Archit Gangwal.
Yes, sir.
Okay, and Bukya Naresh. So I accept all.
Yeah, you can accept all at once. Once you have like 15, 60, 70 requests, you can accept in one tap everybody's request.
Okay, so I
you
accept
can
all.
either wait or you can accept one by one. That's your choice, sir.
So there is a better method. So there is a better method. You can simply share the code of the team from the settings
Yeah,
tab.
but I don't know how to guide sir to generate a code on an iPad. I know how to do it on laptop.
Sir,
But-
where you are on the pending request, aside a channels option will be there, then a settings option is there. Under the settings, team code option is.
No, so I opened my laptops and whatever request I'm receiving, I'm accepting. I don't know whether they are added or not.
So in the laptop from where you are taking the request, pending request,
Mm-hmm.
aside that there is an option channels and after that settings.
For some reason, when I accept, it's showing some problem because of the internet or.
So should I share my screen and show how to generate a code?
Yeah. That will be helpful. So for that, I need to stop sharing.
Yes, sir.
Okay.
Yes, sir. So can you see my screen?
No, not yet. Yeah, now I can see your screen.
Yeah. So in Teams on the laptop, you go to the team, and then here menu and manage team.
Then menu, manage team. Okay.
Yeah. So for example, I made this made this team, and then manage team. No, sorry, not this one. This one. Yeah. So manage team, and then here settings.
Settings.
And then the team, there will be an option of team code here.
Okay, so team code. I click on the team code.
And then you'll have to generate. If it's not generated, then you'll have to generate it.
Generate. Okay.
And then copy it, and then you can send it on the same group. So then you won't have to accept the requests.
Okay, so this code is 0Q. So just the code.
Yeah, so you can just copy and send it on the chat or on the WhatsApp group.
I'm sending on the email. Just the code, right?
Yes, sir.
Yes, sir.
That's all it's needed.
So S3, S4, S5, S6, and S7. Okay, so the subject is code. So now I have sent the email. Can you check whether you have received it?
Yes, sir. Just a minute. I'm refreshing. Yes, sir. We did. I did receive the email. 0Q4CJOE.
Yes.
Okay, I've received the. I think everybody has. So
Yes,
now
sir.
they can direct. So now you won't have, if they use the code, then you won't have to accept the request. They can directly enter. and if someone uses the link, then you'll have to accept the request.
Okay, so now everybody should be in. So just try to use the code and get in the team. So is it like they have to do this, put this code every time they enter
No,
the
sir.
team?
Once they're in, then whenever you start a meeting, they'll get a notification, and then they can directly join the meeting.
Okay. So can you do it now in the next 1 minute? Before we
The
finish?
code you shared is for 629, I think. Not for 001.
Wrong team is shared.
I have used. Oh, I have
Wrong team.
wrong team.
Yes, sir. 629. MAN 629 is shared.
629. I have shared this one. Oh. So let us do it again. So this is. But I have a couple of members here now. And then you said go to. Okay, I have to do this on laptop, right?
Yes, sir. 3 dots and then manage team and then settings.
So teams. Manage team. Setting. Then team code. Generate team code. Okay. Copy. Send it again. So now I'm sending the new code. So it is sent.
Good afternoon. Can you guys hear me? Can you guys hear me? Okay, let me check. Cannot unmute. Let me check if there is any setting issues. But I have how the setting has changed. Class. How can I unmute? I don't know. Is there any setting issues? How come this meeting is locked? What I'll do is I'll send a fresh link. Is that okay? just like event. So that has a different settings, and that's what it happened. Don't know how to stop this sound, because when there is a new attendee joined, there is a beep sound. I'm not able to fix that. If anyone knows that will be good. So and see, if I lock the meeting, probably it will be difficult. So it doesn't show here. Breakout system, invite, meeting settings, polling, question set.
Sir, on the top left, there is a meeting option.
Yeah.
There, meeting settings and then notification.
Acha, okay. Notification, I can join meeting, that part is sound. So this we should make it. No, this was off anyway. It was participant action sound.
Yes, sir. Beep sound off करना है वहाँ से.
So I should uncheck it.
Yes, sir.
Yes, sir. You'll have to uncheck it, and then the beep sound will stop.
But it is unchecked. But still the sound is coming. That is weird.
Sir, for both joining and leaving, you can uncheck, and for chat also.
Yeah, these are all unchecked right now.
Yes, sir. So now we are good to go.
Okay, probably. Let's see. It's fine. So, okay, let me start sharing something and then. Okay, so first of all, welcome to IIT Roorkee. Probably you guys are still in the virtual mode because you guys have not reached the campus yet. And hopefully by next semester, you guys will be allowed to come to the institute. I hope like things gets better as time progress, and we'll meet like physically very soon. So the course you guys might have already informed that has a different part, and it is an introduction to engineering physics or physical science, because there are two batches, like engineering physics batch as well as integrated MSc batch. So the course structure may be like it is a little bit of structured in the sense like you can have some coherent lectures, but in reality it may not be the case. So every faculty will try to sort of illuminate light on some particular areas of physics rather than physics. I would say like more like applied physics. And definitely there are different areas in physics, right? Somebody may be interested in some basic science, somebody may be interested in some applied field and so on. And also when we talk about the applied field, there are vast areas. I mean, definitely cannot restrict within a few lectures, okay, this is what the physics is. So what I'll try to give you some sort of an overview is in today's, I mean, like in the 21st centuries, we all know that the energy demand is there, but the supply is not much. So there are two ways to tackle it. Either you generate a lot of energy or you save energy. So both can have a big impact. So there comes the lighting part, because without light we cannot do anything. In daytime probably we'll be able to work, but nighttime definitely we don't have. I mean, like if there is no light, we cannot work. So that means your work hour also will go down if there is no light. Especially like in tropical countries, we don't because here we have almost like 12 hours of daytime. We don't feel like we are okay. We have to work more. But if you go to slightly like the northern hemisphere or the southern hemisphere, the daytime and nighttime will change depending on the kind of the season you have. Maybe during summer you can have more like longer daytime, and during winter there will be very short winter. A very short daytime. So then what you can do is, if there is no light, you need artificial lighting, and that's what the lighting becomes so important in this civilization. Now, in my lecture, I'll try to give you some sort of an overview of solid state lighting. And solid state lighting, when we'll talk about solid state lighting, next would be the light emitting diodes and the lasers, because the lasers and light emitting diode, they are quite there is a similarities. I mean, although the working is slightly different, but unless you know the light emitting diode, you cannot work on the solid state lasers also. But couple of lectures I'll try to focus on the lighting, which is basically solid state lighting, and little bit of the material aspect, like what are the materials used for solid state lighting, what are the properties, and how to design some high efficiency LEDs and so on. So that's what I'll be doing in next two classes. So let us start with the very introductory part of it, like so as I said,
this
like
beep sound is still coming.
yeah, I maybe I need to figure it out how to do that. All these things are unchecked. So, okay, let me just go back to the settings again. So if I meeting info, right? No, this is meeting info, not the meeting settings. I was trying to figure it out, but I'm still because all this.
Sir, in audio and video, you can get
Video settings, switch to audio. No.
audio and video.
No, there actually I checked it. See, as I said, like all these things are. Let me just try one more time. Meeting, then settings. Notification. They're all off. No, this beep sound is not coming, right?
So there is a drop down list
That's a different one.
in the notification.
Audio,
section.
let me check. Audio bell test. No. These are all off. I think still it is going. Okay, it's now fine. I think most of you guys have already settled down. Yeah, go back to the presentation again. So as I've said, right, the lighting actually starts long time back. I mean, like if you look at the civilizations, even like much before, like we think about it. I mean, it started like sometimes like 500,000 years ago, like first torch, 70,000 years ago, like first lamp, things like 1000 BC, first candle, 1772, gas lighting, and so on. So these are some of the lights probably already people have been using. We are most famous about the Edison lamp, which is started much earlier. And here you can see all this history starting from like some civilized centuries, like 1800 centuries to 1900 centuries, and so on. Now, okay, definitely like some of them are not so efficient at that time, but still good enough to do a lot of activities with this light. And later on, like starting 20th century sometime, we are more sort of focused what kind of light we are choosing, what is the quality of light, what is the energy consumption of light. So we started thinking about other aspect of light rather than okay, light, we need light to work. Rather than that, we started thinking about the efficiency of the light, energy savings of the light, and so on. And that is where the compact fluorescent lamp came into the picture. And that time, like this is supposed to be the energy saver, and it has been known commercially like energy saver because you can have the same intensity of light using CFL rather than say incandescent lamp. So it was going on for almost like 10-15 years, and suddenly this light emitting diode come into the fixtures. And then the CFL technology also nowadays sort of obsolete. I mean, you may still see some old lamp, but no one is not, no industries are not making the CFL lamp anymore. Now in 21st century is all about the solid state lighting, and that's what the lighting technology come into the picture. I say lighting technology means we need to also understand the economic aspect of it, whether it is really beneficiary or not. Now, if you look at the overall consumption of power, you'll see like almost like 21% of the electricity is used in lighting, right? So that means whatever we generate, some gigawatt of power, or like if you look at the global perspective, it's almost like more than terawatt of power. The 21% of that electricity goes to generate light. So now, if you start saving energy by using efficient solid state lighting, definitely you will be able to save a lot of energy. And if you look at the market, you can see like projected financial savings almost like more than $100 billion by 2020, right? And also, like if you look at the energy payback time, because the LEDs are so efficient and their lifetime is so long compared to the say incandescent bulb or fluorescent lamp is even lower than incandescent bulb. So so then definitely people started investing more into solid state lighting. Apparently, when this technology came into the market, they were slightly expensive than the CFL or other incandescent lamp. Maybe you can buy like a 40-watt bulb with like 50 rupees, or maybe you need that same amount of energy to generate. You need to pay like 200 rupees of LED bulb and so on. So overall, there is a little bit of expense at the beginning, but because the lifetime of these LEDs are much higher compared to the incandescent lamp or fluorescent lamp, people started investing more into solid state lighting. And then I would say like last 10 years, probably the solid state lighting has got like a really huge market, not only in India, but in across the globe. So you can see the projected like from 2010, like last one decade, you can see the kind of rise this LED market has compared to these previous years, right? And if you look at the efficiency, initially it was like incandescent, then there are some halogen bulb, halogen lamp, which are supposed to be higher efficient than incandescent lamp. Then fluorescence come into the picture, almost like 80 lumen per watt. We'll talk about all these efficiency parameters and so on. But at that time, the white LED was not so efficient. Probably that is the reason why fluorescence become so popular at that time, like early 2000s, right? But later on, 2020, 2010, these white LED which are available in the market, they are almost like comparable, or rather, maybe slightly lower than that. So around like 6 to 11 per watt. But we are expecting that it would go up, and now this has jumped up to close to 100 lumen per watt, or maybe like 90 lumen per watt. Nowadays, if you go to the market and buy light emitting diode or white LEDs, it will be written like say 900 lumen, 90 lumen per watt, or maybe like 100 lumen per watt, close to that. So this is the trend now. Now, definitely, the luminous efficiency has gone up over a period of time, and that is not only for the color LEDs, which were initially very bright or very high, like red, yellow, green, and blue, but nowadays white LEDs also has very high efficiencies. So that is the reason nowadays all these lightings are based on the solid state light. So also at the same time, you can see the lifetime of these LEDs are also quite high. Initially, it was not so high. It's the measured one. You can see the lifetime was not so high. So it is claimed that it would have very high sort of lifetime. So initially, it was not high, but nowadays, all this lamp has very high or a very long lifetime. So even if you invest at higher price, it can last for a long time. So its payback time is quite short in that sense. Now, what is the technology? If everything is so far, everything is done. So what is the technology people are still scouting or people are still working on? So definitely, like most of the LEDs nowadays you do see in the market are basically the inorganic LEDs, but later on people started looking at more cheaper and more easily like some materials which can be easily manufactured, because all these inorganic LEDs are expensive, and then you cannot make very large area devices. So you can make a pixelated one and then arrange them, and that's what you can do. But nowadays there are some technologies like say organic LEDs or like perovskite-based LEDs, which can be solution processed. You can make on a large area substrate, and that is what the new technologies are coming into picture. So then the challenges are to improve the efficiency beyond like whatever at this moment the efficiency we do have. Efficiency of light generation, improved efficiency of light extraction. So one of the biggest challenge in light emitting diode, especially for like surface mount light emitting diode, maybe in next class updates I'll be talking about, because all these organic or inorganic materials, inorganic semiconductors we use, they have a very high dielectric constant, and then you have air. So high dielectric to air, there is a huge dielectric mismatch. So then what will happen is most of the lights are trapped within the device itself. They don't come out of the surface. So then how to improve the light extraction efficiency? This is what one of the bottleneck. Maybe I can use the separator. So this is one of the bottleneck why the external quantum efficiency is not high in some of the LEDs. So these are the challenges in recent years, like people have been trying to address, and I mean, like people are addressing some of these challenges. And definitely the cost has to be reduced. So at this moment, as I said, like if you can buy say 40 watt of incandescent lamp at a much cheaper price compared to say 40 watt of LEDs, they are much more expensive, right? So the cost has to be reduced. So these are some of the challenges. Now, what exactly LED light in compared to the other light source we do have, like say incandescent lamp, or say compared fluorescence lamp, or maybe some other light source like mercury vapor lamp or sodium vapor lamps. There are different light sources generally we do see in our day-to-day life. Definitely the quality of light we get from different sources are very different. So to understand or to classify what kind of light source it is, we need to know different parameters, like what is radiometry, what is photometry, and what is colorimetry. So these are the three different areas in like where we can talk about the measurement in different aspect or different perception, we can say. So when you talk about the vision, like what our eye is sensitive, then we'll be talking about the photometry, right? That means like what we do see. And like it doesn't matter what wavelength it is coming, like how I perceive the color, that is what the photometry is. Now you guys might have basic knowledge of like biology in your 10th standard. Probably you guys know like how we see things in our eyes. So there are two types of photosensitive photosensitive cells, which are known as like rod cells and cone cells. Cone cells are sensitive to the colors, or you can see like that has a photopic vision. Normally at high intensity, cone cells are active and you do see different colors. So now if you look at the responsivity curve of cone cells, it gives like this. So it will have a response from somewhere 400 to maybe like somewhere like 530, 540 is the maximum. That means eye has sensitive towards green much more than the blue or the red. So if you have the same intensity of blue or red color or green color, we will see the green is more brighter than blue or the red color, right? So that is what our eye sensitivity is. So definitely whenever we design some sort of a light source, we have to make sure that in our eyes the colors are much more brighter. So our sensitivity, eye sensitivity matches with the light source itself. Then when you go to the low light intensity, that is known as the scotopic vision. Scotopic vision is basically when the illumination intensity is very low, we do not see or we do not perceive the color of this object. So we can see some sort of object is there. It could be like more like a gray color. We can have, generally we don't see the depth perception as well. You can just see okay, there is some object, but you cannot see like what is exact the color, what is the depth of this object, and so on. So this is known as the scotopic vision. And cone cells are basically red, green, and blue sensitives, right? So this is what the eye sensitivity is. Now in radiometry, what we do is basically we talk about the output power of the source. In photometry, we talk about the intensity we perceive in our eyes. So that is what there are two things, like one is radiometry, one is photometry. So probably in some courses it will be much more clear. So there is an advanced course in MTech. Normally I used to take that course like solid state lighting. There we talk about details about the radiometry and photometry. So in radiometry we talk about like watt, like it could be electrical power, like watt, or we can talk about the watt per nanometers. That is the radiometry what you call units. But at the same time we can talk about the photometry, like what is the intensity we perceive in our eyes. So that is normally known as the luminous flux. We can talk about the luminous intensities. So sometimes it's also given by lumen per watt. So these are the similar parameters. Although if you look at the dimensionality, there could be similarities, but because they are used in two different contexts, one is the source, other one is the way we perceive the intensities or the yeah. So that's what there are two different ways. One is radiometry and one is photometry. And when we talk about the colorimetry, that's the mixture of all these things, like what is the wavelength and so on. Now in solid state lighting, we are more interested in the luminescence. That means what is the intensity coming out of some source. Source could be the point source could be extended source. For example, like if I talk about a very small bright LEDs, they are like a point source. But if you look at the tube lights or maybe some other light source, which can be like the illumination is coming from the surface. So that could be a extended source of light. So definitely when we talk about the luminescence, we need to talk about what is the flux coming out some per unit area or so on, right? So sometimes it is given in terms of like candela per meter square, sometimes it's given like in terms of lux and so on. So there are different units. So when we talk about the radiometry, we'll be talking about the candela per meter square. When we talk about the photometry, we'll be talking about lux. So that's what in photometry we'll be talking about illuminance. Illuminance is basically lumen per watt or lux. So or lumen per meter square. Sorry, lumen per meter square. That's the lux. Right? And if you look at the sunlight, like what we get on the Earth surface, that varies somewhere like 10⁴ to 10⁵ lux, depending on the cloudiness. I mean, if there is clear sky, at noon, probably you'll get more than like 10⁵ lux. If there are some cloudy weather and sometimes like a dark cloud, even it can go down to like 10⁴ lux and so on. And if you look at the like moonlight, this is somewhere like 0.1 lux. You can see the difference between the sunlight and the moonlight, the intensity difference. That's huge. Right? That's what normally in night time you don't see color. You always your rod cells are active. You only see the object or perceive some object, but you don't perceive the color. Now, definitely, like depending on kind of activity we do, right? So, for example, like I'm reading in my room, like what kind of intensity we do need, or I'm working in some very small. I'm working with some very small object I need to see, or some object I need to see. What kind of light we need, and so on. So, what is the light outside during daytime? What we get. So depending on the kind of what work or kind of activity we do, we also need to design. So this is another part of like the solid-state lighting technology, to design a light source which are more efficient, as well as like you don't feel like, okay, there is less light or something like that. And also we'll be talking about the purity of the light. Like for example, if I take say incandescent lamp or LED lamp, they will have a different color spectrum, right? We'll be talking about the correlated color temperature, the color rendering index, and so on. So these are very rich physics behind it, like how we perceive color. It's not that easy that okay, there is an object, we see some color. It depends on also like what light source we illuminate with it, right? Whether we illuminate with the white LEDs or some like sodium paper lamp or some mercury paper lamp. The color it appears will be very different depending on what kind of light source you choose. And that's what you can also quantify or classify the light source based on the color it appears, right? So that we'll be talking about sometimes. So normally like in a public space, like people are just roaming around, you don't need very bright intensity. I mean, you need only very small illuminance or low intensity of light, so maybe like 30 to 100, right? But if you are working in some residential areas or maybe some industrial areas, commercial areas, you sometimes need bright light, or maybe like 300 to 1000 lumen per meter square, or maybe you can say like 300 to 1000 lux. Some special visual tasks, including those with very small or very low contrast critical elements, we need even much brighter light, maybe 3000 to 10,000 lux. So depending on kind of work we do, we need to choose the illuminants. And definitely if you have more illuminants, that's maybe sometimes it's of no use. So that is what the lighting design is very essential for efficient use of energy. Now, so now what is the difference between now colorimetry? Because color comes because of the wavelength of the light source we do have. So there are some international organizations. We basically there are some different organizations we basically have, like whether I mean, depending on the, just a minute. So this international organization, what they do is like, if I have some color, how do I classify what color is this, whether it's purple, green, blue, or what kind of color is this? So to match that, there are some functions which can be defined in terms of mathematical formalism, and that is what comes into the colorimetry course. So you can see, like, if you have some sort of a wavelength which is very sensitive to blue, so definitely if that matches with the x coordinate, x will be maximum, but then y and z coordinate will be 0. So I can take any function and split into 3 different function of like x, y, z, and then classify what is the weightage of x, what is the weightage of y, what is the weightage of z, right? So if I see like x, y, and g, they are all equal, like 0.33, 0.33, 0.33, that will be pure white color, right? And CRI will be 1. And if the these parameters are slightly like it's more like x, y, and z is equal to 0. So ultimately, sum of x plus y plus z has to be 1. So if one of them is high, other two are not, so it will have definitely a different color, and that is what we'll be talking about, the color coordinate or chromaticity. This is known as the chromaticity coordinate, and you can have a different color temperature, different color rendering index. So that means like we can define any color in a mathematical formalism rather than having some wavelength functions. We can have some mathematical formalism, and that is known as colorimetry. So don't mix with the calorimetry. That's a different thing. This is a colorimetry.
So
Yeah.
I have a doubt in the previous slide, sir.
Yeah.
So the graph is what versus wavelength. On the y-axis, what's on the y-axis?
So y-axis is basically the intensity.
Okay. Intensity in the unit.
Any arbitrary unit. So any function can be normalized. You can have any arbitrary unit, and then like you can like basically like you can normalize them, whatever the weights. So if you have some sort of a spectrum, right? Now, how do I split into these 3 coordinates? So I have to define these 3 x and y and z. So probably this next slide will be more clear. So what this CIE, this is some international organization which does this chromaticity coordinate. What they do is like, if I have some color, can I define using some sort of a coordinate? So now, as I said, like x plus y plus z is always equal to 1. So if I know x and y, right, then I can define what is z. So z becomes sort of redundant. So then all these color can be mapped into a coordinate systems here. Like this is known as chromaticity coordinate. So definitely there are all these mathematical formulas. We'll not be able to discuss in details in a couple of classes. So this is to give you an overview that color can be coordinated. Like you guys might have been doing like Photoshop or some other softwares, right? Any photo editing software.
Yes, sir.
And you guys might have noticed that there are different color numbers you can put. For if it is a RGB, you can define what is R percentage, what is Z percentage, what is B percentage, like red, green, and blue percentage. So if you choose a different percentage of RGB, you get a different color.
Yes.
This is also the mathematical formalism of color. This is what the colorimetry is. And the chromaticity coordinate is defined such a way that any color can be mapped on these diagrams. So you have some sort of like parabolic curve here, and then there is a straight line here. So it starts from blue, this is green, and this is red. And if you go to the center of this coordinate, you get green. Oh, sorry, pure white color. So if you go towards this side, you get more green. You go towards this side, you get more blue. You get towards this side, you get red. And some wavelengths which are like sort of monochromatic, you can get these are the colors like 400, 460, 480, 490, some color. So these are sort of like pure color. They are not the mixed color. So the boundary of this chromaticity chart gives you the pure color. But if you have to get any color in between, that will not be a pure color. That will be a mixture of 2 colors. So it cannot get the pure color of like somewhere like here. If my coordinate is here, I cannot get a pure color. It has to be mix of like I can get like green and blue with some percentage to get that. So maybe let me just draw some
Sir,
lines.
is this the spectral locus?
Yes, sort of. You can call it. Yeah.
So it's in the two-dimensional form, not including the z-axis, which has the luminosity.
Yes. So why I said is because if you know x and y, you can find out 1 minus x plus y is equal to z. Right. So for example, like if I have say R, like simple example, you can have the RGB. So these things has been used for in many classes. Like your color printer also use the R.
Yes, actually, I'm into photography, so that's why I know luminous locus.
Yeah, exactly. So depending on
thank you, sir.
This is 0.3, this is 0.3, and this is 0.33, or maybe like 0.33. So then you get this part, right? So any color in between, like if I say like I need any color, I'll mix this color and this color with some ratio of these two. So this loci will get some color mix, so you get this color, right? So that's what like x plus y plus z is equal to 1. So if I know these two, then definitely the third coordinate is basically redundant, right? So that is what this color like chromaticity diagram shows. Now from the chromaticity diagram also you can see these are some numbers written. These are known as the color temperature. So color temperature has some sort of a like significance, because if you think about the black body radiation, or this is also known as the Planck'sian locus or black body radiation. So if I know the temperature of the black body, I can get some sort of a color spectrum, right? So if I get some color, I get some sort of a so it is why it is wiping out, I don't know. So if I know the temperature of the black body, I can get the color of this body here, right? So, and that depends on what is the temperature, right? So definitely increasing temperature there will be a blue shift, decreasing temperature there will be a red shift. So that is what you can see. This is like color temperature 2000. So if you have a the black body which has a body temperature 2000 Kelvin, this is definitely in Kelvin. So you get a color which is quite similar to the coordinate here. So if you increase the temperature of the body, it goes to somewhere here and beyond that. So if the temperature of the body increases, it goes toward like more like a bluish color rather than like reddish color, right? And sometimes when you buy commercial LEDs, you might have seen like warm white or cool white. Warm white is basically your low temperature, because its color is more towards the red, whereas the cool white is more like a high temperature, color temperature. This is also known as correlated color temperature, CCT. So higher the temperature, it will be more like a bluish white. Right? So these are very important aspect of the solid state lighting. What kind of light source we'll choose for different applications, and that's what whenever you design any LEDs, you need to also calculate the color coordinate, because that also gives you the purity of the color. So if it is on the Planck'sian loci, it is like more pure color. If it is away from the loci, definitely it will have a different color. So the color rendering index will come into the picture. We'll talk about maybe color rendering index sometimes. We'll see like if I can get some time today itself. So if the point is not on the Planck'sian locus, definitely the color rendering index will be very different, right? So in a standard CIE source or CIEs, definitely there are different point. You can say commercially you can get like 3000 color temperature, or maybe like 5000 color temperature. So these are different source. You can see like A is the tungsten at this temperature, tungsten lamp. This is basically like a Planck. This tungsten lamp will have like a Planck'sian source or black body radiation. This is the direct sunlight, approximately like 5000 K. That's the sort of purest you can think about on the earth we can get. That's the 4870 Kelvin. Overcast sunlight, that will be even higher temperature. That's more like a bluish color. D65 daylight, this is a different source, equal energy source. So these are all like equal energy source and so on. So these are some of the natural light source which will have color temperature on this Planck locus. Now, if I design any LEDs, it is very difficult to put it on this locus. Definitely the color spectrum will be very different than this spectrum itself. Now, when we talk about the white light, it is nothing but the mixing of the many colors. I mean, definitely, like when you look at the rainbow colors, so there are so many colors mixed in a different percentage, and that's what you get the purest white. But you can generate the white light just by mixing red, green, blue. So this is your red, green, and blue at a different percentage. So if you mix red and blue, you get this color, sort of like pink shade. You get red and green. It might be very, it's not very intuitive. Like if you mix these two colors, you get yellow. You guys can try at home, like take two LEDs of red and green and just focus on some particular point. You will see it will turn out to be yellow. Now this is a yellow color which is a mix of R and like red and green, and you can have another yellow which is pure yellow, like maybe 580 or 590. That can be another yellow. So definitely our eye will not be able to distinguish whether it's a mixed yellow color or a pure yellow color, right? Same as like sand color. If you mix like blue and green, you get some sort of sand color. And again, you can have like 510. That's also a sand color. Maybe like 500 to 510. I would say like somewhere this would appear something like sand color. Or you can have blue and green mix. You can have sand color. So some colors can be monochromatic, or you can have a mixture of that. So this is what, when you mix RGB at equal percentage, you get white light source. And that is what, when we design the, it's not only the cameras, not only the display technology. Nowadays, all this white light source you get, commercially available white light source, they are also mixture of like all three colors at a different ratios. And then you can control the color temperature, you can control the color rendering index and so on. So by mixing three different colors, you can also have a multiple of that. Maybe like we'll be talking about how to design the white LED source and so on. So you can have more than that. Like this is the simple one. You can have even CYMK, cyan, yellow, magenta, and black. So CYM, these three also you can add up, and you can get like white color. So depending on how to mix all these colors. Why it got hanged? It's not moving. Okay, my PowerPoint actually got crashed. Just a minute, my PowerPoint got crashed. Because it's writing too much. Right? Okay, so definitely, as I said, like to get the white light, like as I said, like you can mix RGB and you can get the color. Now the question is it only the RGB, or we can mix just two color and get the white light? Now here is one shaded area you can see. Like if I take this one and this one, the depending on what is the intensity I choose, like blue and yellow, I can get white light source here. So I can draw any line here, and then I can take two points on this things, which will be passing through this the point here. And if I can adjust the intensity of this two light source, we can get white light source. So this is the color mixing from this this international diagram, and that is the way we can design the white LED. It could be purely two LED source itself, or it could be one LED and then one fluorescence. So there are different aspects of that. Or you can have a very bright blue emissions with the yellow and green phosphorescence or fluorescence. We can mix different ways to generate the white light source. Now, as I said, like the perception is very important here. Like what we perceive in our eyes is very important here. So I can take any light source, I can mix these two colors, and it may appear like white source, but in reality is not. Like if I have like sunlight, I can see any color at a purest form. Like if I have red, green, purple, or whatever color source you do have, I can see that very purely. But if I take any other light source like LEDs, I may not be able to see all the color very purely. So then there is a concept called color rendering index. So ideally, if the source is very uniformly distributed, or the white light source has all this wavelength present, then I should be able to see any colors. And then we can call it the color rendering index is close to 100 or 100. Now, if I take two colors and then in between I don't have any other colors, so then any object which has some particular set of colors, maybe like if I just give you some sort of example, that I can take two colors of say here and here, right? So maybe this is where like your 510 cyan color, and this is somewhere like say reddish color like 670 or something like that, and somewhere the green resin is not there. So if I have any object which is somewhere here, this color source will not be able to reflect that, because the object will not reflect any color from this part, because there is no color itself. Although when these two colors are mixed, it may appear the white color source, but the object which absorbs somewhere here and emits somewhere here will not give you any color. Then it may appear like very dark color. But if I have another source which is very broad, something like this, right? All this spectrum are present, then I'll be able to see that color, right? That green color will be able to see that. So that means this white source and this white source, they are not exactly identical. This can give you all this color, like what I want to see, but this will not give you all this color what I want to see. So then the color rendering index of this source will be high, very close to 100, and this will be much lower, right? So here you can see like light gray is red, light blue is green. So there are different colors, there are different spectrum, and if I have to see, I mean, there are different color gamut. I mean, like there are different method. Again, there are some standard rules. Some cases they use like 8 different color gamut. If all the color gamuts are looking same, then it will have CRI 100 or like uniform. But if out of like 8 color gamuts, some of them are not looking good or equal, then definitely the color index will come down. Same as like you think about like say sodium maple lamp, definitely it will not give you the very good color contrast. Same as like when you go to market, probably it is very common. When you go to market, especially like those who buy like clothes and other things, right? You go to some shop, buy some clothes, knowing or assuming that okay, this is the color. You come back home, and the next day morning you try to see the color. It may appear very different. and that is because the light source they are using at the shop may not be pure white light source. So that means the color appears there is very different than the color when you see under sunlight. That is what the color rendering index becomes so important. So I think I'm already running out of time for today. So I'll keep discussing on that. Like this is very fascinating. This area of like understanding the color and like how the light sources are designed. It's very fascinating. So those who are interested, definitely like you can. And solid state lighting nowadays also like very big thing, especially like big industries and especially like designing efficient light source. Like it's very promising, I would say. And apart from that, like how to design efficient, low cost LEDs, light emitting lasers and other areas. So I'll stop it here. If you guys have any questions, queries, you guys can drop a message or email to me.
So can we get the slides in a
Yeah. So what I'll do is I'll share this slide in the MS team. So
thank you so much.
Can, because a lot of things I will not be teaching. So then what you can do is you guys can read for yourself.
Okay, so it also helps in revising after the class as well. So
yes, sure. So that will.
Thank you so much.
Anyway, because this 2 class is not nothing. I mean, just to give you. So the idea of this course is to give you the overview. Whichever you are interested, you can go in details, read more, because this is the beginning of your like 4 years journey. Right? Whichever interests you can grow more interest on that. You can learn more about it. Right? So I'll put this slide in the MS team, and I don't know